Yo, what's up, everybody? Welcome to another live learning session. Um, Today, we're going to cover how you can build a basic neural network in PyTorch. So this is just building the neural network here. Everything we're going to do is just with the Torch NN namespace, and we're just going to basically be using the NN module. If you want to see an more advanced usage of the NN module, I wrote a little bit about how you can create your own interface with encoder decoder models on that, and I'll link that below as well. So we're going to build a neural network to classify images on the Fashion MNIST dataset. I'm also going to link the original page for this tutorial. It's written by PyTorch. I did not write this tutorial. So let's start. We're going to import OS, import Torch. And then we're going to start importing modules from PyTorch. So Torch is the PyTorch package, and we're also going to import specific modules, named modules, so that we can access them in an easier manner. So from Torch import NN. I don't know why it was doing that. From torch.utils.data. Import data loader. Yeah, data loader. So this is going to be what we use to load the data set, probably. From Torch Vision. Import. Oh, do I not have Torch Vision here yet? Okay, so I'm going to have to pip install that. Datasets and transforms. So I have Torch Audio. I've written a couple tutorials on Torch Audio, but let's pip install Torch Vision. Okay, so probably using a different version of Python than before. So what we're going to do here is we're going to take this code and we're going to move it up here. I'm going to Yep, okay. See if I can run that in this package. So let's see what kernel we're using. I'm using one of my 3.10 kernels. And this current one, my base one, is actually in 3.9, so that's why I don't have it. Okay, so we import these. And then we're going to find out what device we're using. Let's see if there's any. Please update Jupyter and IPy widgets. Okay, so let's update those as well. Pip install -u Jupyter IPy widgets. So we're going to comment this line out. Let's do that. Failed to load image Python extension. Okay, yeah. Symbol not found. This should be okay. Okay, let's try this. Okay, there we go. Now let's get our training device. Device equals CUDA if Torch CUDA is available. I don't think I have Torch CUDA. I have a Mac, so CUDA is available. Dot is available else CPU. And it should tell us that we're using CPU. Print f using device. Yeah, that's what I thought. Now we're going to define a class. So this is basically how we start the encoder decoder model example as well, as defining an interface with 2 points, the init function and the forward function. Module. So def init self def forward self. Okay, so now let's write the init function. So we're going to do what we did, exactly what we do in the other one, in the encoder decoder model example. And now we're going to change up some stuff. So flatten equals neural network dot flatten. Oops, that's not right. And then dot flatten. Now we're going to make a ReLU stack. So this is the linear ReLU stack. This is kind of like how the sequential model will look. And then dot sequential. This is basically the layers in your neural network. Oops. And dot linear. So let's get rid of this for now. And then dot linear. 28 by 28. 512. So this is the input. So the MNIST fashion set is going to be a 28 by 28 matrix, basically. Here, 512, 512. What is 28 by 28? 784. Yeah, 784 pixels. It's 28 pixels by 28 pixels on each side. And dot linear 512, 10. So you should note that this number matches this number, and this number matches this number, and that's because when we pass, well, I'll also link the neural network tutorial below that I wrote. But basically, when we pass between neural networks, the size between the layers has to be the same, unless you're building an encoder-decoder model, which I will link as well. So forward takes an x, which is the input. So first we're going to flatten the input. Oh, this should actually be x. Yeah. Oops. Logits, yeah, nothing else. So this is the neural network model. This is way simpler than the building the neural network from scratch that tutorial that I was talking about earlier that I wrote. You can check it out and compare for yourself. This is like way less lines of code. So let's put the neural network onto our device. Let's just do that, yeah. Device equals device, basically. And then we'll print out the model. Aha. Whoops. Oh. Not a module subclass. Yes, okay. Yep, whoops, I fucked up twice. Okay, well. So basically what we do here is we just want to pass the model the input data along with some background operations. So let's try this torch dot rand 128 28. So this gives you 1 by 28 by 28 x input matrix. So once again, we're not calling the forward function directly here. We're not passing the matrix into the forward function. We're just calling the model on it. So actually, the init itself should take, yeah, okay. Predicted probability. And a softmax. Yep, softmax. Dim equals 1. Yep. Y pred equals pred prob dot argmax 1. And then we're going to print the prediction. Class y pred So this is basically what the predicted class is when we pass it a random set of 28 by a random. Let's also print X out so we can see what that is. But this is just a random matrix, as you can see. Okay. Now let's try again. 3, 28, 28. Print input image dot size. So basically this is a mini batch. This means that we're putting in 3 28 by 28 images. Now what we can do is we can flatten these images into 784. So instead of getting a 28 by 28 vector, now we have a string, 28 by 28 matrix. Now we have a vector of 784. So flatten equals nn dot flatten. And we're going to flat images equals flatten input image. So actually we can probably just skip this and just do dot flatten input image. So we should probably also make this input images, but this should show us, whoops, and then we just need to see the flat image dot size. Whoops. I see. Okay, so actually what we should do is not that, because this is the reason why we should do that. Okay. And then dot flatten. So this means that we're going to call, wait. Size. Can I print this? I'm playing around a little bit with n and flatten. Okay, so flatten doesn't let you call size. What if I do this? Okay, flatten equals nn dot flatten. Equals flatten input images. Print flat images dot size. Okay, so pretty sure. Now I'm curious. Print type flat images. Torch tensor. Okay, so what about flatten? That should be function. Okay, print type and then dot flatten input images. Okay, interesting. So if you call nn.flatten on a set of images, well, can you do this? Can I do this? Torch.tensor. I see. Okay, so that's what we should. So nn.flatten. Basically, what we're doing here is actually this. Yeah. Okay. Cool. Just curious. Anyway, now let's check out the layer model so we can get an understanding of how that works. The linear layer applies a linear transformation. So let's take a look into layer 1. Features equals 20. So basically what this does is it converts a 28 by 28 image into a 20, like a vector of size 20. Okay, so yeah. Now let's also take a look at what ReLU does. So we'll print the layers before ReLU and then after ReLU. ReLU is regularized. What does ReLU stand for? Regularized linear unit, I think. Rectified linear unit, sorry. And then we're gonna this is an interesting, like, because you're passing data into the function call, but you're not passing the data to the function. It's an interesting mix. It's an interesting like differentiation. So nn.flatten actually creates a function, and then you can pass parameters to that function to have it operate a specific way, and you can also pass data to the function to have it operate onto the data after ReLU hidden one. Cool. So what does ReLU do to data? Let's take a look at what ReLU does to the data. It looks like it takes all the negatives and makes them 0. I think that makes all sense. Yes, everything else is the same. Now let's also look at what sequential does. So sequential basically puts a bunch of modules in sequence. So let's take a quick look at what this does when we run it. So seq modules. And dot sequential flatten. Oh, I probably should have made the flatten. Okay. Well, yeah. Well, let's do dot flatten. I probably should have just made it flatten. It's probably easier to do that, but you know we're already here, so. Oops. Layer 1. And then dot ReLU. And then dot linear 2010. So what we're doing here, layer 1, so flattens the 28 by 28 to a 784. Layer 1 turns 784 to 20. This doesn't do anything, 20 to 20. And then at the end we're turning a 20 into a 10. So I think we can just use the flat images. Input images should be fine. I don't think we've touched input images, so we can probably just use input images. And then let's do logits equals seq model module input images. We should print module, print logits. We don't have to build a module again. Cool. So that's basically what it looks like for these things. These are the values for the images. These don't mean anything right now because we're not training them to mean anything, basically. But now the last thing we're going to do is basically do softmax, which does it's another transformation, and it turns the logits into 0 to 1. So the logits, as you can see, are kind of all over the place, and now we're going to put these into 0 to 1, kind of like ReLU. So we're going to use softmax and 1 dimension. Oops, 1. Pred prob. Softmax. logits. Print. Oh, we'll just do this in the other one. Print prom. Cool. See, now we have the logits moved into 0 to 1. Now, what happens when we actually train? So initially, you have random hyperparameters, but as we train, we get different parameters. So the way we're gonna see this by taking a look at the example parameters in the beginning. Wow, this tutorial does not actually teach you how to load the data and put in the data, but we're gonna load the data. So this is from here on out, we're just operating with 0 guidance. But we'll take a look at the structure first. Model structure, model. Let's take a look at this. And now we're also looking at the name and the parameter. For name parameter in model.named parameters. We're going to print layer name. And then parameter size. And finally, values. And this is number 2. Cool. So this is kind of the initialized, randomly initialized values. Now let's load this data set. So I think I'm going to look up how to load the Fashion MNIST data set with PyTorch. Wow. I mean, Torch Vision. How do I load it? It's actually kind of wild how little tutorials exist on this. I would have expected this to be pretty easy to load. Okay. So let's go to training data set. Equals data loader, or data sets, whoops, probably. Data sets dot Fashion MNIST, yeah, okay. Can I just load this into, like Fashion MNIST as like a data root? Okay. Oh, I have to download it. Here we go. I wonder how big this is. Oh wow, this is a pretty big data set. Well, it's not that big. It might take a while to train though. It's okay, we've got a few minutes here. Oh, there's okay, there's a lot of things to download. I'm gonna look at how big this data set is on my Mac. Personal data space, PyTorch, GANFL. Oh, it's 87 megabytes. That's not that big. Okay, this is fine. Anyway, we're gonna do a train split validation ratio of 2 to 1. So validation ratio equals 0.2. Oops, 0.2. Oh, sorry, not 2 to 1. 1 to 4.2% is gonna be validation ratio. So now we're gonna be train is gonna be a train train num, I guess. Yeah, the number of things we want to train is going to be minus validation ratio. And we can just put 0.8 here, but really we can, we probably want to, we want to len MNIST. Ooh, what did I just do? I want to turn this cell into oh, here we go. Let's make this Python. Okay, there we go. I don't know what I pressed there, but I pressed something weird. Cool. Valid num equals the other len ist minus train num. Nice. Okay. Now we can get the train data, valid data. All we do is really just extract the data sets from the ratios. So torch.utils. Oh, I should have data sets, shouldn't I? Torch.utils. Do I have that? Okay, I don't think I imported that specifically. So I'm going to publish my own tutorial on this because it doesn't seem to exist, which is kind of weird. Anyway, probably need to do validation too. Let's get let's do the test. We're gonna have to split out the test objects too. Or can we just get the? Oh, geez, I have a. Yeah, we're gonna need a test ratio too. 0.1 minus test ratio. Okay, I'm just gonna validation ratio times len MNIST test num equals int validation our test ratio times len MNIST. Okay, and then test data test num. Is this the best way to do it? I don't know, but I don't have anything to follow, so we're just gonna make stuff. We're gonna make stuff up. As long as it works, we can optimize it later. So let's look at train data.size. Subset attribute has no subset. Okay, what the hell? Type data. Can I turn this into a dataset? What if I do this? What if I do this here? Probably want to move this up here actually. Transform equals transforms dot to tensor type data. Okay, so that doesn't actually help. Train data dot transform transforms dot tensor train data. I don't know how to actually call this. Okay, transform subset to tensor. Can I just call it torch.tensor? Torch.tensor. Train data. Train equals. Can I just do this? Only one element tensors can be converted to Python scalars. Okay, so how do I call transforms dot to tensor PyTorch? Let's read the documentation. Converts a PIL image or numpy.nt array to a tensor. So it doesn't quite work this way. So it converts one PIL image at a time. So we probably need to do this for each of them. So what is my, let's see, type train data. Oh, I need to go somewhere soon. Oh no. Okay, so maybe we'll do the training next time. It's also been over 30 minutes. Okay, so we'll do the training next time. Okay, make sure you subscribe. See you guys later.